this is an illustration of group velocity. You have this cosine here, this cosine here, and their sum. We have wave number for the one, wave number for the other one, frequency and a second frequency, and you can see that although the waves themselves advance at a certain phase velocity, for example, if you take a look at this point has its own velocity. The group velocity, which is represented by this point, which you can see has the same velocity of the envelope, is different from the phase velocity. And I remind you that the group velocity is just the ratio of the difference in frequency and the difference in the wave number. Let's see if I can tweak it such that the phase velocity is totally opposite to the group velocity. Let's see if I can get it. Yeah, I think that's it. You can take a look at what happens when I move just a little bit. You can see the phase velocity moving at one direction, moving to the left, but the group velocity, the point, moves in the opposite direction. Another point to consider is what? Yeah. If the k's are equal, well, that's the case if they're almost equal. You can see that the beats become very, very wide. But if you go even closer, oh shit, if you go even closer, you see they get really wide. And if you make them, and the closer they are, of course, the smaller the denominator of the group velocity is, and the higher the group velocity becomes. And when they're exactly equal, the group velocity is infinity. This is exactly what happens at an electrical Kirchhoff circuit. The group velocity is infinite, which means that when you have some circuit and change at some point, the change or the information about the change is considered to be transmitted immediately throughout the entire circuit. So this is what an infinite group velocity looks like.